Hello all, welcome to this video lecture. Well, in our previous video we discussed about the k-means. Now, as we saw in k-means, the number of clusters must be determined in advance and the convergence is highly dependent on the initial central point setting. So we need to think about the non-parametric technique, and typical non-parametric technique is the mean shift clustering. Let us start with this example. Here we have these billiard balls. These are the points and these points are in 2D. Each point has x and y location and we want to find the densest region or the most dense region of this distribution, and we'll start with some initial estimate randomly, or we call this the region of interest, and this region of interest is defined by this blue circle, and we take all these points within this blue circle, and what we do is we estimate the center of mass here like this, and the center of mass is shown by that small orange circle, and it is estimated by taking these points, add them up and divide by the number of points, which gives us the centroid or the center of mass. Now we will find the shift from the previous estimate to new, and this shift gives us vector from previous estimate to the new center of mass, and this vector basically is called the mean shift vector. So what we do is, here we take some initial estimate, just start with some initial region of interest, then find the center of mass, and we shift the region of interest again there. We get the we shift the center of mass, region of interest there. Again we estimate the mean center of mass there, and we keep on shifting again and again. Then we keep on doing it and find the centroid until that converges, or we find the mean shift vector to be 0. So this process gives us a mean shift vector, and how that mean is the shifting, and once it converges, that is the region where we have the densest set of points. So the mean shift vector, the way it works, that is, we are given data points, approximate the location of mean of these data, and we want to estimate exact location of the mean of data by determining the shift vector from the initial estimate, and we'll do it iteratively until it converges, or until the mean shift vector is 0. So we just keep on doing this until it converges or the mean shift vector is 0. So let's see how we do it. Suppose we have the set of points data here, and this is our starting point here, this y0, and here we compute this mean shift vector. The way we gonna compute is, first we find the mean of these points, and these are the points x1, x2 up to xn. We have n points, and we sum them up, and these are the vectors in the case of 2D vector. This is in this case it's 2D, and they can be of any dimension. We sum them up, we divide by nx and the number of points, and subtract it from the initial estimate of y0, and the mean shift will essentially point towards the direction of maximum increase in the density, and which is the dense set of points. As we see here, here is the start point. This is here this is our start point, and it points towards a direction. We will keep going and until it converges, or where it will it won't move further, like it will move towards the direction. It starts from y0 and it moves towards the direction of y1, and it will converge. It will stop only when this ms will be 0, and it will not move further. And the mean computed here is equal to the it's the equal weighted. We can see here we estimate with the equal weight with 1. All of the samples, all of the points are equally weighted. And the better way to do is that here we can see we can better way to do is we can assign the weights to each points here. That is, this xi can be assigned with some weights that's based on the that is with wi, and this wi may depend on the distance from initial location y0 to the point, and we can apply the weight and then define the average. And since we are applying the weight, we will sum them up and normalize by the nx. Then we subtract y0, then we will get this mean shift, this one, like we subtract with the we subtract this estimate with this normalized this average with the initial estimate, and we get the mean shift. Here nx gives the number of points in the kernel, and y0 is the initial mean location, x0 xi is the number of these are data points, and h is the kernel radius. Like this h will define how big this circle will be. And usually the weights are determined using the kernel mask, and uniform, it may be uniform or Gaussian or or Epanychnikov. And if we look at the properties of the this mean shift and mean shift vector, this mean shift vector has the direction of gradient of density estimation, which is important, and we are gonna use that. We're gonna use that, and it's computed iteratively for obtaining the maximum density in the location of local neighborhood. And this process is actually very good to estimate or find the modes or the peak of the distribution. And as we have said that this is very good for it's very good tool for finding the modes in a set of data samples, and that manifests an underlying probability density function PDF in the given data set. Like we said, we have used this term probability density function. This is the widely used probability density function is Gaussian probability density function, Gaussian, and which we can say is the parametric distribution. This is used in statistics when an assumption is made of the way like the underlying data is distributed. So when we know the property of the underlying data distribution, and an example would be a variable is assumed to be normally distributed, all subsequent analysis will rely on this assumption, and the parameters associated with this assumption like mean and standard deviation contribute to the analysis. While in the non-parametric case, in non-parametric distribution, the assumptions about the pattern or the form of the underlying probability distribution function from which the data are drawn are not known, which are unknown to us. So given the kind of distribution, given this kind of distribution or the non-parametric distribution, the mean shift is good for analyzing the this distribution or non-parametric distribution. And the idea here is simple, that there is no equation for the distribution. In case of non-parametric distribution, we don't know the equation of this distribution, so essentially we will store all the samples we have. And the advantage of parametric distribution is that we don't have to store all samples like in parametric, like in case of Gaussian or something like that. We don't have to store all the samples. Once we have parameters of the distribution, or like the covariance or the mean vector, however we can estimate the probability of the given random variable. However, we have no model arbitrary distribution, and we have to store all the samples in non-parametric, like in our case. So the problem is if we have millions of samples, then it would be a time consuming, or it will take lots of time. So now we are going to look into that like this non-parametric distribution. And like we can see here, we have this distribution. We have this data which has lots of points in 2D, and the distribution look like this. Like we can see here, the distribution in the left side, which looks like Gaussian, but we do not know the exact distribution. Now we want to use the idea, like now what we want to do is we want to use but we want to use this mean shift and find the gradient of this distribution. So essentially we will find the peak of the mode. We say this peak, or we can see here, like we have got this non-parametric distribution, and what we do is we use this we use the gradient estimation mean shift, and we go for the PDF analysis. We go to the we go to the peak. We try to find out the mode or peak of this by taking the some estimate and find the mean, and we shift it to find the mean shifted, and keep going and so on, and until we reach to this peak. And suppose like let's see, this is our real data analysis. This is our real data, and again we have points here, and each point has the value x, and in x and y it's 2D, like it has some point, it has some value, it's in 2D. And if we look at so it has this kind of distribution. It has two peaks, the one big peak and another one is small peaks, and it has this kind of distribution. It also looks like mixture of Gaussian, but we don't know the parameter of this distribution. So we need to know, we have to find out the peak here, and here we should be clear what we mean by the distribution. So we have to know first of all what is the distribution here, how this distribution works here, and then we will discuss in more detail about the mean shift. So let's see a simple example. Let's be clear about distribution. We have got this image here. Like let's take a simple example. It is the histogram. Like histogram is also a distribution, and let's see just a very simple example of histogram. And we take image, suppose it's 32 by 32 image. We have total 1024 pixels, and each pixel has some value from 0 to 255, and we can get the distribution of histogram. Like we will have 256 bins from 0 to 255, and then every bin contains the number of pixels in 32 by 32 image, like which are 0, like the number of pixels that has value, and 2, and so on. And if we put these numbers, that becomes a histogram. We can see here this as the histogram, and these bins give us the number of pixels in this with this value, like with 127. What is the number of pixels that has this point gives us the number of pixels that has the intensity value 127, and this becomes, if we put all these numbers, that becomes the histogram, and that is also a distribution for the particular image. So while it's a simple distribution, and it's also non-parametric, because we are not fitting some particular model like Gaussian on it. We don't know the parameters of here. It's just the distribution. We don't know any parameter about here, and we don't fit any kind of distribution like the parametric distribution like Gaussian and some other distribution, because we are looking for the and it has one dimension, because we are looking for the intensity value, because it's only for the 1D. And here in this case we have 2D, and we are looking at x and y location of each point. So 2D distribution on the right, like it's so for this on the right we have actual data points like this, the real data samples, and on the left it has the distribution. So they are the different things, like we have got the real data and its distribution is given by this underlying PDF. So in order to represent or estimate this density distribution, we are going to use what's called the kernel density estimate. Here, for represent this, we have to find the density estimate, and we call the kernel density estimate. This is the probability density function, and we will be in terms of samples. Like the samples are mu1, mu2, and to mu n, and we will have the function which is Gaussian, and it will be defined on it will depend on x, and this PDF for x, the probability PDF for x will be depend on the this x and this mu I. And given a particular value of x, what is the probability that we will encounter in this distribution, we can compute that using this formula here, this formula, and which is saying that we look at the distance x from all the sample points. So we look at the distance of x from mu1 and distance from x to x from mu2, mu3, and so on, and the proportional to the distance from x, we are going to take the exponential and we will add up these things, and basically this we estimate this PDF based on the distance, exponential of the distance of the point from its given data points. And basically finding the probability of particular x will be all points, like all points will contribute here, and the contribution will depend on how close they are to the x. Like if we have the distance, then if it's far from the, if the point is far from the sample, then it will the value it will contribute so that what we have is this distance, and this is called the density estimation. We will estimate this density here. And while estimating the density, the important thing is the kernel. So as we saw before, we were having a kind of Gaussian kernel, that this kernel will tell us that depending on the distance from x to the data point and how much weight we are going to assign, and here we did is exponentials like Gaussian. We can have different kernels as well, like here we have the normal kernel, or which is the Gaussian kernel, another one is the uniform kernel, and another one is the Epanychnikov kernel. As discussed earlier, in the normal distribution, normal kernel, which is Gaussian kernel, it will depend on the distance or x square from and exponential and the constant. And while in the uniform kernel, in case of this uniform kernel, what happen is we will apply uniform weight. Whatever the distance, the weight will be same, and the weight is constant for all. And another one is the Epanychnikov, which is quite little bit different from these two. So this is our kernel density estimate for the non-parametric distribution. As we have seen before, we essentially want to compute the probability given any value x, and the way we are going to compute is that we have the samples x1 to xn from x1 to xn, these are say points. We will find the distance from it and apply the kernel and add it up, and the point which are very far from x will have very small weight. So the simple way to represent density function which are not parametric, that is, we don't know it's Gaussian or mixture of Gaussian or anything, but we have to this all endpoints, and maybe these are the millions or millions of times, and then then it will become a big problem. Now what happens is, like, now let's see the relationship of kernel density with the mean shift. So here first what we do is we gonna differentiate it. We are finding the gradient and the derivative of this probability distribution function. We have this PDF, and we get the we get the derivative of it, and since this is the square, we have the square here, we get the derivative will get the 2 and x minus xi here, and another is the k prime, which will give us the derivative of this k, and this is the gradient of density, which is expressed in terms of kernel and k prime. And so given that we are going to use this notion that we are going to call this as a k dash as g, let us just change this k dash to g, and we have here k prime, which is g of this, and xi minus x, this xi minus x. Then we are going to get two terms with all the constant terms, this xi minus x, gx minus xi, and here, and like if we just simplify this, we just multiply this gx minus xi square with xi and with x, and we get this term, we get these two terms. And if we more simplify it, we take this outside. What we do is we take this g x minus xi square outside, and we get this term, and what we get here is g minus x, this g x minus xi, we call this as the mean shift here, like this term. This we represent it with the gi, and what we find is this g xi gi and summation of gi, it can be represented like we can say it as a we mean shift, and mx is the, and total and this is the this is the initial estimate, this is our initial estimate. And what we do is we get the this mx gives us the mean shift vector, this whole term gives us the mean shift vector, and here we obtain the mean shift, which is gradient of the probability. Like this term, this is the mean shift, which is the this g like this gi gives us the gradient, and here what we obtain is the mean shift, which is gradient of probability density function, and which is in the non-parametric form. And so what we can say is that this mean shift is the process we described. We start with something like with the x some point, and we find the mean, and we shift it and keep on shifting. By we do this iteratively, and we keep on shifting and until we find the peak, or until it becomes the until this value becomes, until this difference becomes the 0. And it's actually finding a gradient of the distribution of the points. Like what we can say is we find the gradient here and of points, and this is how we find the mode or the which is the peak. Like what we do is we just keep on finding the gradient, or we keep on finding the difference here, and we keep on finding, we do it iteratively until we find, until this we can see here, this is our, like until we find the mean shift vector to be 0. Here we can see this color code gives us the very good example. Like this x is our initial estimate, and we find the new mean here, which is given by this orange square, and this estimate. And what we do is we find the difference and change our center and change our and we change our region of interest, and we keep on estimating, or we keep on estimating it repeatedly until we find the, until it converges. And in this way we find the peak or mode of the distribution function, or we find the densest, the most densest region of this distribution.